Alright, I think we're ready to get started here. So, good afternoon everyone. I'm Michael Pardo. I'm going to be talking to you today about Kotlin, how it's going to make you a more productive and happier Android programmer. So Kotlin is a statically typed language targeting the JVM. It's backed by and created by JetBrains, and they are the company bringing you Android Studio and IntelliJ. There are a few core tenets that Kotlin lives by. It aims to be concise, so reducing the amount of code it takes for you to achieve something. Expressive, making your code more readable and understandable. Safe, removing the possibility for you to create errors. Versatile, targets a JVM and JavaScript, so you can run it many places. And interoperable, so what that means is you can call Java code from Kotlin and Kotlin code from Java, and they aim to be 100% interoperable. But why not wait for Java 8? So let's take a look at the history of Java and Android and their relationship. In 2006, Java 6 was released. A couple years later, Android 1 was released as an alpha. And 4 years ago, Java 7 was released. Android followed up with Java 7 support 2 years after that. And last year, Java 8 was released. So when do you think we'll get Java 8? It might be a while if we do get it at all. Even then, if we do get Java 8 support in the next couple of years, it's going to be a while before everyone can adopt it. So this is the breakdown of Android right now, and Java 7 is only supported for API 19 and up. So this is your user base for Java 7 apps, which is just over half. It's not great. And even if we had Java 8 right now with 100% compatibility on all devices, the language itself has some problems. So we'll go over some of those. Null references, coined by its inventor as the $1 billion mistake. You can code very defensively, but null pointer exceptions sneak into everyone's code, and it's just because Java's type system is not safe. Raw types. So we've been stuck with raw types in order to stay backwards compatible, and we should all know how to avoid raw types, or that we should, but their inclusion in the language is kind of misleading and unsafe. Java has covariant arrays, so you can do something like this. You can create a string array and an object array, and then assign that string array to the object array, and it compiles fine, but once you try to assign a number to that array of strings in the runtime, it's going to throw an exception. Java 8 has higher order functions, but they're implemented with SAM types. So SAM is single abstract method. So every function type needs an interface correlated to it. And if you want to create a Lambda function that doesn't exist or doesn't have a function type, you need to create that function type as an interface. Wildcards in generics, so anything but non-trivial generics can get kind of out of control and hard to read and write and understand. And checked exceptions, so these are like exceptions in the method header, in the signature rather. So they're good intentioned, but a lot of time what you'll see is a code base littered with try-catch blocks and ignored exceptions. So let's see what Kotlin does about all those issues. And for pretty much all the issues that we just went over, Kotlin just removes those features. And then it adds a whole bunch of other features. And we're going to cover most of these later. Kotlin can keep moving forward with the JVM ecosystem because it doesn't have any restrictions. It compiles right down to JVM bytecode, which means no overhead. It looks to the JVM just like any other JVM language. And in fact, if you use the Kotlin plugin for IntelliJ or Android Studio, which you should, there is a bytecode viewer, so you can see, click on a method header and see what JVM bytecode is being generated for that. So let's have a look at some basic syntax. I'm going to go over a lot of this stuff pretty quickly, but don't worry, we're gonna go over it in more detail later. So here's the simplest form of a Java hello world. It's just a function and a print statement. There's no package declaration. There's no imports required. This is all that's needed to start up a Java Kotlin hello world. Functions are declared with the fun keyword, followed by the function name, and then the arguments in parentheses, just like Java. However, in Kotlin, you put the argument name first, followed by the type, separated by a colon. And then the function's return type is last instead of first, like in Java. So here's the signature of the main function. If a function doesn't return any useful type, it returns a unit as the type. And we can infer the unit in most cases, or in all cases of a function. So we can just omit that return type for units. And then we print hello world. This just calls into, this is a standard function in the Kotlin standard library, and it calls into Java's system.out.println. So next we're going to extract the world portion of that string into a variable. This is how you declare a variable. It's the var keyword followed by the variable name. And then Kotlin also has string interpolation, so we can include that variable right in the string without having to concatenate it. And the way we do that is just by including the variable name prepended with a $sign. So next, let's expand this to check and see if the arguments that we passed in have any strings. So if this string array is not empty, we'll take the first string and assign it to name. Like so. We also have the val keyword, and what this is it's analogous to a final variable in Java. So this is a constant, and we run into a problem trying to compile this because we cannot rename this constant, or we can't reassign a value to this constant. So the solution to that, or a solution to that, is to use an inline if-else block. So if-else blocks, a lot of blocks in Kotlin can return a value. So what this does is it goes through the if statement and returns arg0 if it's not empty, else it will return world, and that assigns that right into the value we've named name. So yeah, this is a conditional assignment block. We can reduce it to one line and make it look like a ternary operator. And we can remove those braces and make it look even nicer. To reduce the visual clutter. So this is basically like a Java ternary operator. Okay, so let's look at classes now. So we've got a class defined using the class keyword, just like in Java, followed by the class name. Kotlin has primary constructors, so we can put a constructor right in the class header. And in that constructor, we can, it looks just like a function signature, so we define our parameters for that constructor, but we can also define them as properties by declaring it as a var or a val. Okay, so let's take our name assignment logic and remove it and replace it with an instance of the person class. When you create an instance in Kotlin, you don't have to use the new keyword. There is no new keyword, so you can't use it. You just create a new instance by referencing the type. So now our string interpolation is wrong. We're still referencing name. To fix that, we can use a string interpolated expression, which is $sign and curly braces in the expression inside. Here's an enum class. Enums are a lot like Java enums, so this should look pretty familiar. And the way you define them is with the enum class. It's a type of class. So let's add a property of language to our person class. In Kotlin, you can have default arguments. So the default value for this argument is language.en, and then we can emit that value anywhere we create an instance of the class. So let's make this a little more object-oriented and add a function called greet to the person class, and that just takes the language greeting and appends the name into a string. Now we can remove a line from our main function and call person.greet, and it does the same thing. All right, let's look at collections and iteration. So here we have, we're creating a list of person using the list of method. It's a standard library function. And we can iterate that list of person using the for-in syntax and call person.greet on each iteration. Or better yet, we can call an extension function off of this person collection and pass in a lambda, so we can iterate it over it that way. And we can reduce it down to its simplest form, removing the explicitly named value and using the provided name value, which is it. And we can move that up into the list of return value and eliminate that value people we declared. All right, we can do a little better and create subclasses for each language. So first we have to make this class open, which means it's non-final. So classes by default in Kotlin are final. So let's create two classes and pass in a default language for each. And we can replace those declarations in the list with their respective subclasses. And here's our full extended hello world, showing off a lot of Kotlin's features. So let's go over what Kotlin adds to Java, what you can expect to gain by using Kotlin. First off, type inference. You've probably seen this in other languages. So this is what a string declaration looks like in Java. We define the type, then the name, and then the value. And in Kotlin, it's a little backwards. You define the name, then the type, and then assign the value. In most cases, though, you don't need to define the type. A string literal here is good enough to infer a string type. The same goes for characters and integers and longs, floats, doubles, booleans, and any other type. So as long as Kotlin can infer the type, and usually that's if it's local, then you don't need to specify the type when you declare the value or variable. Yes. So in cases where you can infer, you have to define the variable with the full syntax, which is like, yeah, with a colon and the type, and then equals, yeah. So one of Kotlin's most powerful features is Null Safety. So we'll go through an example. Here in Java we have a string. We've assigned null to it. As soon as we go to print that string, though, we run into a problem at runtime, and that's going to be a null pointer exception, because we're trying to access a null value. So this is the same code in Kotlin. Here we declare a null string, but before we can get any even further, we encounter an error with the compiler. The problem is we're trying to assign a null value to a non-null type. So in the type system, there's nullable types and non-null types, and the type system recognizes that this is a non-null type and prevents compilation. So to make it nullable, to make any type nullable, we add this question mark to the end of it, and that means that it can be assigned with null. So now we can continue, now that we've fixed that error. And just like in the Java example, we print the length of the string, but we run into the same problem as in Java. This string could be null. However, in this case, we run into it at compile time instead of runtime. And that's because of the type system. So the compiler throws the error. And to fix this, we need to prepend the call, or append the variable, with a question mark, and that makes it a safe call. So this, what it does basically is it checks to see if the value is null before accessing it. If the value is null, it returns null. If it's not null, then it returns the actual value. So since this value is null, null is passed to the print method, and we print out null. So this is something you might see in Java. We're accessing a value with a ternary operator. We check that the value is not null, and then we can finish the assignment using the value if it's not null. Otherwise, we need to use something else. So the left-hand side is it passed the check, it was not null, so we can access it. The right-hand side is it was null, so we need to do something else. In the Kotlin, you can do the exact same thing. If A is not equal to null, then you can access it. Otherwise, return your default value. But there is a shortcut for this called the Elvis operator. So here we do an inline null check using the question mark, and if you remember, it'll return null if if A is null, and if anything on the left-hand side of the Elvis operator is null, it will use the right-hand side. Otherwise, it will continue with the evaluation. Okay. Kotlin has a feature called smart casting. So if a local object passes a type check, you can access it as that type without explicitly casting it. So here's an example. We check to see if x is a string, and if so, it prints the length. So here's the type check, and we use that using the is keyword. It's like kind of like instance of in Java. And since it passes the check, we can treat it like a string anywhere after the check. It also works in reverse, so here we check if it's not a string, and if it's not, we return out of the function. However, if it is a string, everywhere after that we can assume that it was a string and we don't have to cast it. Casting anywhere after the type check even includes inline logic. So here we're checking if it's not a string, and then we use the OR operator. So if the left-hand side was false, it was a string, that means we can access it as a string, and it gets casted by Kotlin. Or the inverse, which if it is a string, we use the AND operator, and so the left-hand side is true, and we can use it as a string using smartcast. And also anywhere thereafter. Same goes for when statements. So when statement is like an enhanced switch statement. Do our type check, automatic cast, type check, automatic cast, and smart cast. Okay, string templates. So a lot of languages have string templates, string interpolation. This is how you might do it if you're used to Java. You would concatenate this apples value in the middle of the string. If you're using string interpolation, you just move that inside of the string and prefix it with a $. And you can also do it with expressions, so you might do something like this in Java. In the middle of that string, we're concatenating an expression of apples plus bananas. But we can move that into the string and interpolate it, and the only thing we have to do there is wrap it with curly braces after we use the $, prefix. Okay, range expressions. So you might have seen this in other languages too. You'll notice that, like, a lot of these features have come from other languages. I don't think Kotlin has really invented anything. Okay. So here's an expression saying that if x, basically is what it's saying is if I is greater than or equal to 1 and less than or equal to 10, then we print it. But what we're really checking is that if it's in this range of 1 to 10. And instead we can create this construct or use a construct that's already created for us called an int range. We pass in the range of 1 to 10, and then there's a contains function that we can call to see if it's in that range. And if it is, we print I. And this can be reworded using extension functions. So 1.range2 creates an int range of 1 to 10, and we can call contains on that. But preferably you want to use this operator, which is ... which aliases over to that range 2. Yes?
Are your primitives objects? Are integers objects in this?
Okay, so that's a good question. Because of the null type system, we can be smart about that. There are no primitives in Kotlin. So there's int, which is integer or a primitive int, and depending on whether it's null or not, the compiler, the type system, knows whether to use a primitive int or an integer. So it optimizes for your case. So it'll auto box any primitive that exists in Java, so long as you're using the right type. So we can also iterate through ranges because they are iterables. So this iterates 1 through 4 and then prints each value. You can use steps in your ranges, so this will iterate 1 through 4, taking a step of 2 instead of 1. You can reverse iterate. You can reverse a range and iterate with steps. You can basically combine a lot of these functions to make range iteration as expressive as you want. You can iterate over pretty much any data type. You can create ranges for any data type. For strings, example, your foobar data type, so long as there's a logical way for it to iterate and you can implement it. The step, however, is defined internally as a number. So, I mean, it only makes sense to use steps as numbers. So you're limited in that way. So higher order functions, a lot of languages have these now, and so does Java 8, but we can't use Java 8. So if you're on Java 6 or 7, this is how you might implement a filter function. So first we need to declare a function interface that takes type T and returns type R. And here's our method. It iterates over a collection using your supplied function and creates a new array list, adding items that pass your predicate. And then here's the function call. You call filter with numbers and your anonymous function, anonymous class. So here's the functional interface, interface argument, the interface function call, and finally the anonymous implementation. And this is pretty much what it looks like in Kotlin, or at least our version of it. And then the call is looks like this. So you'll notice that there's no interface defined here, and that's because Kotlin has function types. So instead of using an interface, we create, or we specify a type that is a function type that takes in a type T and returns the type Boolean. And then we can invoke the function just like any other function. And we pass in an anonymous function, which is a lambda, that matches the function type that we defined in our filter function. So here's our complete function call. We filter passing in a list and a function. And in Kotlin, if the last argument is a function type, we can declare it outside of the argument list, which makes for some nice clean syntax, which you'll see in a minute. Since function type can be inferred from the function signature, it knows it only has one argument, so we can remove it, and it'll name it to the predefined name of it, and we can reduce it to one line to make it more readable. So inline functions go hand in hand with higher order functions. So let's look at our filter function again. In certain cases, usually when you're using generic types, you can add the inline keyword to the function, and during compilation it will take the lambda that you provide to that function, and it will move it inline into your code. So it'll take this and change it to this, and this is what it looks like compiled. This also means that we can do other things that are not possible in regular functions. So for example, here's a function that takes a lambda, and you can't return out of it. It doesn't make sense, so that's not allowed. But if we make that function an inline function, now we can return out of that function because it's in line with the rest of the code. And inline functions also allow us to use reified types. So here's an example of a function, a real function that we use. That is, it takes it finds a view parent from a view that matches a type T. There are some problems with this function, though. So we can't check the type because generic types are erased. And right here, even if we could check for that type, we'll get an unchecked cast warning. So the solution is to take our function and add this reified keyword to the type. And so because that function gets compiled down to inline code, we can now check against the generic type to see if it's an instance of that, and we don't get a cast warning anymore. Okay, extension functions. I think it's one of Kotlin's most powerful features, although it's not immediately obvious. So here we have a utility function, and it checks to see if we're running on lollipop or greater. And it takes an integer as an argument. But we can change it to an extension function by prepending the type and a dot before the function name. And you'll notice that it looks a lot like how you would actually use the syntax. So we remove our argument, and we need to change that code argument, since we removed it, to this, since we're calling the function on the integer itself now. And this is how we use it. So we can call the function directly on the integer. And it can be any integer, it can be a literal, and it'll still work. So a practical application of this in the standard library here's an example. So, yes? Yeah, so he asked if you can do it on final classes. Yes, you can, and that's because it doesn't actually add any code to the class. You can't modify any class after. What it does is it creates like a static method that looks like the original one, but has this syntax sugar that looks like it's like an actual function of that class. And I'm going to show you an example of how they actually do that in this code sample. Yes? So yes, if it matters where you define that method, it doesn't. It just has to be defined in a package that you are currently in. So if you define it in the package foo, then you have to be nested in that foo package. You can declare it without a package, and then it's global, so then you can use it anywhere. Okay, so Kotlin makes use of extension functions in Java collections. So here's an example of taking a collection and doing some operations on it, some functional operations. We take the list of customers and we map it, and then we filter it, and then we sort it. But notice that in order to do those functions in order, you had to nest them inside out. And it's very messy, and the formatting's not great, and even if it was great, it's still confusing because you're doing everything backwards. And that's where extension functions come in handy in the standard library, is that the extension functions for collections are actually using the Java collections. So you can use your plain old Java collections, and they will statically add these methods to them. Again, it's syntax sugar. So we start with our list, and in order, now we can map the list, and we can filter the list and sort the list. It's very readable. It's still using Java collections. It's not modifying anything. Kotlin makes properties a language feature. So here's a typical Java bean class. We've got our private members, our getter methods, our setter methods. It's just 3 properties, and it's a lot of boilerplate. So Kotlin can do better. Here's the same class in Kotlin. You just define class members as variables, and these are public by default, module public by default, and the encapsulation is taken care of by the compiler. So it's encapsulated in Kotlin, and it'll generate the getters and setters in Java. And access and assignment in Kotlin just looks just like you're accessing a public property, but they're well encapsulated. Kotlin classes can have multiple constructors, just like in Java, but in Kotlin you can also have a primary constructor. So here's our class from the last example, and now we've added a primary constructor, which just is a constructor that goes in the class header. So we can immediately use those variables to assign to our properties of this class, or we can move that into an initialization block. Or better yet, we can just define them as properties in the primary constructor. And we can format it nicely like this, or at least I do. So now we have a class that takes in all those arguments and their properties that have getters and setters. If we change those properties to values, now this class is immutable, which makes it ideal for the functional type programming that we saw earlier and for concurrency. Okay, singletons. So, yes?
On the constructors, do you always have to collect 3 arguments, or is it so automatically generate?
As many arguments as you wish. Yeah. Yeah. It's just like a regular constructor, but it's like the default constructor. The idea behind this, I guess to give a little history, is originally there was only one constructor, and it was the primary constructor. You couldn't have secondary constructors, and the way to pass different arguments was to define optional parameters or default parameters. So like for email, the last one could have been null or empty, and then I would only have to define. I could define 2 variables in the constructor or 3. This didn't work very well with Android because views have 4 different operators now, or constructors now, and so you need to be able to use all of those because the Android OS, the runtime uses all of those. So recently, because Kotlin is becoming so adopted on Android, they decided we really need this feature. So now this is what used to be the only constructor is now the primary constructor, and you can have secondary constructors that look different. But in most cases, the primary constructor is good enough. Especially now that there's an annotation called JVM overloads that will take this constructor and turn it into 3 constructors that builds up. So ideally, like a view constructor will look like this: a primary constructor that has context, attribute set, and default style. And you add JVM overloads, and it'll create all 3 constructors. That's all you need to do, and you need to call super and pass those on to the the inherited class's constructor. Yes?
Will this work with constructor injection?
Yes. So there's a bit of a different syntax if you want to annotate the primary constructor. Basically, between the first parenthesis and the class name, you add all your annotations, and then you, because of that, then you need to add the constructor keyword. So it'll look like class customer at inject or space at inject space constructor, and then the rest of the constructor. Any more questions about constructors? Yes.
So if we wanted to help extend this out to a subclass, we would also define 3 parameters like header, value subclass, and adapter, right?
Yep, you could do that. So if you wanted to subclass this and have the same amount of constructors or more or less, you could do the exact same and then pass in whatever this needs to it. Yeah. Okay, so singletons. So you've likely come across a singleton pattern. Usually you see it in things like loggers. And in Java, there's several ways to implement a singleton. And over time, the canonical definition or defined way to create a singleton has changed. And the reason is that there's no like general affordance for singletons in the language. Here's another way, and another way. And this seems in Wikipedia to be the standard way. I didn't think so. In Kotlin, this is a singleton. So you just create an object at a package level wherever you want it to be scoped, and you can access this object anywhere as a single instance. And a more complete example would be this logger singleton. So you would access this function d as logger.d, and it's available everywhere, and there's just one instance. So to tie into that, we have companion objects. So Kotlin removes the concept of static and objects and methods. So to get around that and to help with interoperability, we have companion objects. So normally you'd see something like this, an activity with a constant string called tag and a static method to start the activity, creates an intent. And you can access the tag statically, and you can access the method statically. And then here's the same implementation in Kotlin. So we have our companion object, which is kind of like a singleton for this class. And inside that we have a string constant for tag and the start function, and then we access it the same way as we did in Java, for both Java and Kotlin. So the syntax is the exact same. Delegation is a pretty well-known pattern too. And Kotlin makes this like a first-class language level feature. So here's a typical Java example you would see. Here we have my special implementation of list. It implements list. It takes a list of the same type in the constructor, so that we can store that list internally and delegate to it. And then it passes the list methods on to the delegate when we want to it, and then we want our special behavior, we do whatever we need. And here's the same implementation in Kotlin. This uses the by keyword. So we implement this list of E, and we take in a list of the same type in the constructor, and using the by keyword we can tell our list to delegate to this variable that we took in the constructor whenever we need to access one of the list interfaces objects. It's pretty useful when you need it. I don't need it often, but it's a pretty nice feature. Declaration site variants. This is kind of a confusing topic, or it can be, so I'll do my best to explain it. So first let's start off with this example of covariant arrays. So this compiles just fine. A string of objects can be assigned to a string, or an array of strings can be assigned to an array of object. But this does not. You can't assign a list of string to a list of object because they don't inherit each other. And if you try to compile this in Java, you'll get an incompatible types error. So to fix this, we use uSite variants in Java, and we define our list of objects as a list whose type extends object, and now we can do that assignment. So you'll see for that reason, you'll see stuff like this in Java's collections, where add-all takes the collection which extends type E, but it returns type E like the actual type. And in Kotlin, you'll see something like this instead. It has declaration site variants, so you'll have to mix up or split out your collections. So this interface is a list that takes in type something that extends type E, and it returns type E. And then we have a mutable list, which takes in type E, extends the list type E, and mutable collection. So now we have a immutable type and a mutable type of collection, and the site variant, or the variance, is much easier to understand because it's in the declaration. So that means in Kotlin you can assign a list of string to assign to a list of anything, even if it's an array list or a mutable list, because a mutable list still implements list. But this is where you run into problems, because a mutable list is not a mutable list of any is not a mutable list of string. And you'll get a type mismatch when trying to compile that because of that. Okay, we have operator overloads. This is our last section. So let's look at an example. So here we have an enum of coin that we created, and each coin has an integer cent value. And then we have a purse class, which has a float value for the amount of money it contains in dollars. And in this class, we create a function called +assign. And so +assign is a reserved function that the compiler will pick up on, and it will call this function whenever you use the +assign like operator. So we create a purse instance, and we can add coins to it now, and that will modify the internal value of amount. And there's operator overloading for pretty much everything, anything you would want to do, really. So adding to your Kotlin to your project is pretty easy. You don't need to do this now, but you used to. What you used to have to do is create a directory alongside Java, so you can point to it in your build config, or your Gradle build config. But now apparently you can just have it in mixed in with Java classes. You'll need to add the Gradle plugin to your build script, and apply the Kotlin Android plugin, and add your source directories, and include the standard library, which you'll want. You should also install the Kotlin plugin to get language support in the IDE. And here's all the resources you'll want to get started. Probably won't need more than this. So the reference on Kotlin's website, tutorials, they have a Quans project that is really helpful. You can go through it like in an afternoon and learn almost everything you need to know about Kotlin. And this comparison to Java is a pretty good place to start too. All right, any questions? Yes?
What are the reasons not use it?
So I wouldn't say this is a reason to not use it, but this is a consideration to make. Kotlin used to not support annotation processing, and now they do, but it's really slow and it adds a lot of size to. Never mind. It just makes your compilation steps slower. So for that reason, for dependency injection using Dagger 2, we still use Java for those, just because we don't need any more compile time.
Is it what things like unit tests?
Yep. Yep. We use Roboelectric and plain old unit tests, and we use Mockito. There are some considerations you have to use when using Mockito. Classes can't be final, so you have to declare them as open. There's not enough to complain about to avoid using it, and we've been slowly switching to Kotlin over the past year and a half. And finally, our code base is like more Kotlin than Java, and so that's probably one of the best features is the interoperability. It allows you to slowly adopt it over time. We started with like our domain data structures and slowly moved it into everything else. Yeah.
You can still debug the whole way through.
Mm-hmm. Yep, it's just JVM bytecode and it's integrated nicely with IntelliJ because I mean they wrote it, so you can debug nicely. We were using retro lambda before, and the problem with retro lambda is the bytecode that it generates is not necessarily the source code that you wrote. So during debugging, you're not going to hit your breakpoints correctly. And yeah.
What about
Jack and Jill. So yeah. So Jack and Jill won't work with Kotlin because it goes from source right to dex, and Kotlin still has to go to that bytecode step. Yeah. Yes.
Should you guys find any problems with reflection?
The only problem with reflection is that it adds another library that is about as big as the standard runtime.
Does it do runtime reflection? So we ran into that problem. We were using Ruby, and we ran into that problem with Ruby that it was doing runtime reflection to get to the lambdas and into some status class analyzers. So
No.
you guys didn't see any like runtime slow.
No, it all compiles just down to JVM code. So I guess so. Like the lambda example is so if you're using function types, it's using its own JVM internal inline functions. If you're using say if you're using RxJava, which has all the function interfaces, it will compile down to like an anonymous class, but you can still use like the syntax for Lambda. So I mean, there's no added overhead. You're just it's less optimized.
It's not calling Kotlin objects at runtime. It's actually just calling Java.
Mm-hmm. Yeah. Anything else? All right. Thanks.